Assalamu alaikum. This is the replacement lecture for last session that we were supposed to have the lecture on the 23rd of October on Wednesday, but I had to cancel it. So this is the replacement slot. I'm going to cover MOS transistor theory, both NMOS and PMOS. So what we're going to do today is that we're going to have a look at how to incorporate what we've studied before. You've done semiconductor devices before this with Dr. Shah, and how we are going to take it off from there. Okay, so hang on, I have this to be a laser pointer. Okay, so these are the MOS transistor symbols. NMOS symbol used in the class is a 4-terminal device which consists of drain, gate and source with a substrate, and the PMOS is the same symbol but with the source at the top, source, gate, drain and bulk. Sometimes it's called well because in a CMOS structure the PMOS will be contained in an N well on the P substrate. Okay, but on paper usually we draw the symbol with 3 terminals, just the drain, gate and source, and even the individual package that you've handled in the labs are usually just 3 terminals, right? Because the individual package would have the bulk and the source tied together. But in an integrated circuit where there are many transistors, many NMOS and PMOS on the same substrate, a common way of tying the substrate is tying the substrate down to the source for NMOS and tying the bulk or well up to VDD. Okay, so the reason is because if you consider this NMOS here, for example, I have the cross section schematics here. Between the N and the P, this is like a diode because you have a depletion region and you want to keep this region here reverse biased. So for the purpose of keeping it reverse biased for NMOS, the P has to be most negative, and for PMOS, if PMOS, the ones here is P plus, the well is N type, so the N has to be most positive. So that's why in a PMOS the well is tied because it has to be the most positive, is tied to VDD, and for an NMOS the bulk, which is P type, is tied down to the most negative, which is ground. Okay, so but on paper we draw the symbol with just 3 terminals, but we know how it is connected. So when doing a simulation or layout design, we must ensure that all are connected accordingly. On paper we just draw 3 terminals, right? Because we already know at the back of our head that if it is an NMOS, the bulk is connected to the ground. If it is a PMOS, the bulk is connected to VDD. But if you are doing simulation, every time you add a device, you will have to tell the simulator where to connect the substrate. So each transistor, also a recap from last lecture, has a defined width and length, or sometimes we call it as beta. Beta here is W over L. Okay, so W over L here refers to the distance between the source and drain, or rather you can also say the drawn distance of the thinness of the polysilicon. Okay, technology. So you have here the polysilicon will determine the channel length. Okay, so L is actually the channel length. Well, there are many ways of stating what L is. It could be a drawn polysilicon L, or it could be L effective, or it could be the channel length. Okay, so but whatever it is between the source and drain. And W, width, is the width of the transistor. So this is L and this is W, and you can see the effect of W and L. Now how big or how small can W and L be? Now L it can be as small as the minimum value of the technology. So if you say a technology is 0.35 micron, the smallest L is 0.35 micron. If you say the technology is 1 micron, the smallest L is 1 micron. If you say the technology is 3 nanometers, you went to the talk in Kuala Lumpur Convention Center the other day, and they mentioned 3 nanometers. So the smallest L is 3 nanometers. Okay. But W here is the width of the transistor. Okay, how it goes into the structure. Now, can you make, if it is a 1 micron technology, can you make L 2 micron, for example? Yes, you can. You can make it as reasonably large as you want, but you cannot make it smaller than the technology minimum value. Okay, so how large can you make it? How big do you want W and L to be? It will have to be reasonably a reasonable value. I mean, if you go smaller, the price is more. So usually you don't make L too big. You can go the smaller size or double, slightly more than the smaller size. It's usually safe. Okay, but it depends on the theme, and throughout your design, usually you keep the L to be the same. Okay, anyway, so what this is saying is that you know that it is a 4-terminal device, okay, and you will have to define in your simulation where the bulk goes to as well. And also don't forget what L and W stands for. Okay, next slide. Alright, so this is a very familiar picture that you get from both analog electronics 1 as well as you've seen this many times in semiconductor devices. So this is the structure of a MOSFET. If I were to go to one before, this is the distance between source and drain, LW. So this striped one is the polysilicon, which is the gate, and the blue one here, the thin layer below this structure, is the oxide, and the structure below this is the semiconductor. Okay, so if I were to take just this middle structure, okay, sometimes we call this the MOS capacitance. If we take just the middle structure, meaning this is the polysilicon, the thin layer here is the oxide, and the section below here is the semiconductor or the silicon substrate. Now when you apply the gate source greater than threshold voltage, a channel is formed. Okay, so if you don't apply anything, you have a P, if this is an NMOS, you have a P-type substrate. Okay, so you have polysilicon gate, you have a silicon dioxide insulator, and the body is P-type. And when the body is P-type, it means that the charge that is in majority in this region under the gate, okay, is going to be P. But just to give you some context here, this would have been the N plus and the N plus, right? So this is the channel region, and if VGS is less than 0, that channel region would just be have a majority of holes, which is the P substrate. Okay, now let me erase that first. Okay, right. So if you apply, if you start to apply VGS, okay, as it becomes more positive and as it approaches the threshold voltage, it starts to repel holes, and then when it increases above the threshold voltage, what you will have is a collection of electrons here. You say that the channel region has inverted. That is what you have been studying all your life as you did semiconductor devices. Okay, so the channel is inverted to have the same majority carrier as in the source and drain. So just now we said that in this region here you have the source and then you have the drain. The source and drain, if for an NMOS, will be N plus. So once you have inverted the channel region, it means the source that is N plus and the source that is N plus and the drain that is also N plus will be connected through a path of a channel that has been inverted, which is also N plus. Okay, when it is inverted to form the channel, there is a path for the channel, for the carrier to flow between the source and the drain. So let me correct this statement for the carrier, electron carrier, to flow between the source and drain. Also to emphasize, again, I'm repeating, this channel region here, okay, once it has become inverted, it means that you have a lot of electrons here, right? If it is an NMOS type, so NMOS, N plus source, N plus drain, and a path which consists of electrons. But if there is no motion, if there is no movement of carriers, then there is no current yet. So what makes a current to flow? What makes a current flow? Okay, it's a drain source voltage that makes the carriers in the channel flow. A charge when it flows, only then it forms current. So in this case, when charge flows, it becomes a drain current. So you have here VGS, which forms the channel, and VDS, which makes the channel flow. So in this case, in this top part here, this is cut off. If there is no channel, then there is no issue of current flow, because there are no carriers relevant to the source and drain, which is N, majority, N plus. Okay, but once VGS is greater than threshold voltage, once you have the inverted channel, you have the channel formed between the source and drain, then it is the value of the drain source voltage that will determine the drain current size traveling, the drain current value that flows between the source and drain. Okay, so the value of VDS compared to VGS minus V threshold determines the operation region. You've also seen this in the semiconductor devices, but I'm repeating it here. Okay, so if you have drain source voltage less than VGS minus V threshold, you have it to be in the linear region. Now, some books call it the triode region. Drain source voltage is a value that you apply. It's because of the circuit design that takes the supply from VDD to ground, and you know how things are arranged through KCL, KVL, and things like that. So whatever value that they get from VDS, this is considered as applied voltage. Whatever value that the transistor receives from the circuit, due to the biasing from the circuit, if it is less than VGS minus V threshold, and again VGS is also a value that is within the circuit, the bias that it gets within the circuit, but V threshold is a value that is characteristic of the transistor. You get that from the manufacturer. It's designed to have a certain threshold voltage. So if VDS is less than VGS minus V threshold, it is a linear region. For example, when you put the transistor in the circuit, and let's say VDS gets to be 2 volts, okay, and also because of the circuit conditions and all that, let's say VGS, which is gate source voltage, to be 1 volt. So VDS is 2, VGS 1 volt, but if the threshold voltage is 0.3, so 1 minus 0.3 is 0.7, 1 minus 0.3 is 0.7, but VDS was 2 volts, so that means it is not in the linear region, it is more than, VDS is greater than VGS minus V threshold, so that makes it in the saturation region. So this is, when you design a circuit, this is what you look for. Okay, because you decide whether you want it to be in the linear region or the saturation region. So how do you decide? Well, it depends on what you want the MOSFET to act as. A saturation region is when the drain current is somewhat not affected by the change of drain source voltage, VDS. But if you want the drain source current to be linearly affected by VDS, then you will have to have it in the linear region. So whatever it is, if you want to know whether it is in linear region or saturation region, you look at VDS compared to VGS minus V threshold. So this is nothing new. You've done this in analog 1, you've done this in analog 2, you've done this in semiconductor devices. Okay, now, because you're now experts, okay, So let's have a look. We're going to do NMOS and PMOS in SPICE simulation. In our case, LT SPICE. We have two simulators. Remember, we simulators that we'll be using. One is LT SPICE, which is a lightweight freeware simulator that we can use on our Windows machine. The other one is Mentor Graphics, Siemens EDA tool, S-Edit and L-Edit. Okay, now let's first have a look at LT SPICE. In our LT SPICE, we can add NMOS and PMOS. So when a MOSFET is added to a simulation, it could be a packaged MOSFET or an integrated MOSFET for IC design. Okay, when you add the MOSFET, if you choose from the list of components NMOS, it will prompt you back with an IC serial number. Which one do you want? Is it the one that is fabricated by On and Infineon, something like that? But this is a packaged MOSFET. It would have to be defined according to the IC serial number. But if it is an integrated MOSFET for IC design, meaning it is not an individually packaged MOSFET that you can hold in the hand, but this is a transistor that is still within the circuit design, which will be fabricated together with other components. If it is an IC MOSFET, okay, where you need to determine the W and L, you choose NMOS or PMOS4 in LT SPICE component, because in LT SPICE, NMOS4 and PMOS4, it has four terminals, which is the bulk for the fourth one. You have to define the bulk, and you can define W and L for NMOS4 and PMOS4. Okay, you will also need to specify the model representing the technology in the simulator. Okay, the technology model refers to the parameters that defines the nature of the MOSFET. That is a result of what the manufacturer has produced. Okay, and the technology model provides the parameters for the NMOS and PMOS that has been fabricated, which I have written here. So when you add in LT SPICE, you'll have your NMOS and PMOS. So let's have a look in LT SPICE. I have an LT SPICE open there. It's a new schematic. You can actually, if you don't like the black background, I don't like the black background, I prefer the white one. You can control that with the color preferences here and somewhere here. Alright, so you can find background, and I have and I have background to be all 255 to be white. Anyway, when you add a component, okay, select component symbol, you will find two NMOS. One is NMOS. If I say NMOS here and I place this, if I click here, it will, if I click the right mouse button, it gives me an option where I have to pick a new MOSFET, and it says which package MOSFET that I can choose here. But this is not the MOSFET that I want. Okay, what I want is NMOS4, and if I put this NMOS here and I click the right mouse button, I can define what L and W is. I can have it, L is 1 micron, for example, width is 10 micron. I can define this. Okay, so you can attempt that. I'm going back to the slides. Okay, and let's touch a little bit on this technology model. The NMOS and PMOS SPICE models are descriptions of the specific nature of the devices having been fabricated by the manufacturer. So there are different levels of description. You can have a simple level of description, for example, SPICE level 1, that's the simplest, or you can have slightly more complicated one, but still very, very simple, the most basic one, level 3. And you can have a more BSIM for level 54 and things like that. But you can imagine if it is a description that is longer, that is more detailed, the calculations will be more complicated and involved. Okay, but you can, whatever it is, you can add the models to your simulation. The SPICE models are provided by the manufacturer for the specific process technology that was used. For example, if you have an XFAB 110 nanometer model, transistor, it will be different from the parameters that are described in ELE554 350 nanometer model, for example. And it will be different from a different, even if it's the same size, transistor sizing, it will be different from different foundries, let's say from Silterra model. So if the person doing the simulation does not provide a model for the simulator, the software will give an error message in LTSpice or use a default model. In some cases where things like Mentor, sorry, I keep on mentioning Mentor Graphics, right? But we are using Siemens because Siemens bought over Mentor Graphics. Now, in simulators like Siemens, Cadence, Synopsys and all this, you need to define the model at the start, because for me to use the model from ELE554, for example, I need to sign documents, okay, which says that, you know, that there are some agreements for me there. So for learning purposes, we have generic models representing typical values in the same format. Apa ni? It means that I don't use ELE554 110 nanometer model, but I use a generic model. For our LTSpice simulation, we'll be using a model that we call CMOS edu_models.txt. This is taken from the textbook from R. Jacob Baker. It's provided in the Google Classroom. I will give it to you. I will upload it there. The parameters are the same, but they're not specifically to a specific manufacturer. It's just a generic model created for the purpose of learning in courses like this. But for our Siemens CDA simulation, we will still be using the generic Siemens 250 nanometer PDK. Maybe if you are doing a more specific course later, we will use we can sign an agreement with ELE554, and maybe we can use the PDK from ELE554. But anyway, for this course, we will be using the generic Siemens 250 nanometer PDK under Siemens, and we choose this PDK when we specify the library definition at the opening of a new schematic design. Okay, so in these expensive tools, we need to give one model technology, we will stick to it. Okay, but for our LTSpice, it's a bit loose. It's a freeware, and we can define it as we go along. So models and simulation still mungkin tak nampak lagi the models and simulation. The models are used by spice simulators to predict how the component will behave under different conditions when connected in a circuit. Okay, so you have a transistor, you want to connect it in a circuit. Now the circuit will have its behavior, you know, it will have the circuit analysis when you want to analyze it, things like mesh analysis, nodal analysis and things like that. And the transistor itself will depend on two things. One is the behavior of the transistor itself, and another is the behavior of the transistor when connected to the circuit. So for example, I have Shockley's first order transistor models here. Okay, now this is an equation, is a formula that consists of terms that comes from the bias in the circuit, as well as it comes from terms that is from the process, as well as the IC design values, which is W and L. So here you have cutoff, linear and saturation different. The equations consist of parameters that are required from the technology model. In this case, beta. Yeah. Nampak tak? So beta here will consist of parameters from the model, from the process, as well as, if IC design, we can determine W and L. When we do our layout, we will determine W and L, where L is the width, is the distance between the source and drain, and W is the width of the transistor. Okay, so this is an example of how the model looks like. It's just a list of parameters. Okay, I've read somewhere that they say if a company takes in a new engineer without any experience, to give them experience, make them develop models. Okay, so this is, for example, this is a model. This is a level 3. This is considered as a simple model, where you have values, which is, for example, thickness of the oxide, you have threshold voltage, you have the capacitance value. Okay, so this is a long channel model. You have Kp here. Okay, some values here, and the equations that you see here are equations that you learned the first thing when you entered electronics engineering degree program. Okay, so this is the kind of model. This is how it looks like, and this is a long channel. That is also still in CMOS models.txt, which is a short channel. We'll have to look at it later. Now you can, when you add the transistor in your LT-Spice, okay, like for example, let's say I want to build the circuit. Okay, this is not actually a circuit which has of any useful value, but it is a test circuit. It's just testing the transistor. You test the transistor to see what the values are like. So I put in the transistor here, I connect the source to ground, I connect the gate to a voltage source, I connect the drain to also the voltage source, and I connect the bulb to also a voltage source. Now what I'm going to do here is that I will sweep what this LT-Spice will say. I will sweep this gate source voltage from 0 to 2 volts when the drain source voltage is 5 volts. So which means I know that there's going to be current because there's drain source voltage, and I would like to sweep the gate source voltage from 0 to 2, and if I look at the value here before, the threshold voltage is about 0.8. So it's going to turn on around 0.8 with VGS. So I'm sweeping from 0 to 2. So it will not be on quite before 0.8. It will be on after 0.8. Okay. So, and I can also state here what the width and length is going to be. In this case, it's going to be 1 micron and 10 micron. And look at this name of the MOSFET. It says this is N_1U. Where is this from? If I look back at the model, this model says if the transistor's name is N_1U, these are the values that describe the behavior. Okay. So this transistor's name is N_1U, and it has the L and W. I want to sweep VGS, and the simulator knows it's supposed to look at this model, because in LT-Spice I have already defined here .include CMOS edu_models.txt. This is just syntax under LT-Spice. Now different simulator will have different syntax, will have different instruction command. Siemens EDA has a different way of defining the library. LT-Spice has a different way of defining the library, because LT-Spice is a freeware kan untuk kita main-main. So dia cara nak define tu pun senang lagi, dekat sini saja. Bukanlah senang, but it is more raw lagi kan. So if you do Siemens EDA, you'll have to define the model at the beginning stage in the library. Okay, so you can also add steps here. You can play around in LT-Spice. For example, I can say not only .dc VGS02, I can also sweep VSB. Now let's have a look at what is going to look like in LT-Spice. But before that, what do I want to see here? When I set this up, this simulation LT-Spice, I want to see the transfer characteristics. Now you studied this in analog 1, but then of course you have grown older and you would have forgotten. Transfer characteristics is drain current versus gate source voltage. Drain current versus gate source voltage. So what is it trying to say? It says that if you sweep the gate source voltage from 0, okay, from 0, and as you sweep, passing through the value of the threshold voltage, only then there will be drain current. So below the threshold voltage, there will be no drain current will be 0. But as you have VGS greater than V threshold, as how we studied just now, as how we mentioned just now, when VGS increases above threshold voltage, the drain current will increase. Here, the transistor is turned on. If it's below threshold voltage, the transistor is not turned on. Okay, so that's what I'm saying. Now, let's have a look. Let's have a look at here. Okay, now I have here LT-Spice. Okay, the same diagram that we had just now. A bulk is connected to the source. Okay, VGS is swept from 0 to 2. VDS is given a value of 5. So let's give this a run. Okay, this is going to be .dc. So I hope you already know your simulation, SPI simulation. SPI simulation, you can do a .op, which gives you parameter value back. You can do a .trend. So if you do a .trend, your x-axis will be versus time. Or you can do a .ac, where the x-axis will be frequency. Or you can do a DC. In this case, we have do a .dc. So I'm going to have ID versus VGS. I know I have to type in .dc when I do the simulation command here. Edit simulation command, I can do a .dc because I want to get ID versus VGS. The y-axis I want to get is ID. The x-axis is VGS. So that's, if it's current versus voltage or voltage versus voltage, it will have to be .dc. So I'm going to add trace, and in this case I want to see what the drain current, so I will choose ID M1. There you go, so I have it there. So in the model it says the threshold voltage is 0.8. True enough, before that drain current is almost 0. After 0.8, the drain current rises. Now, if I take this circuit and I bias VDS to be around 5 volts, and if I take this transistor, sorry, not this circuit, if I take this transistor and put it in a circuit where VDS is going to be 5 volts and VGS is 2 volts, I will expect that the current will be 600 microamps. Okay, this is how it works. I do not use this circuit in its form, but I'm going to take this transistor and I'm going to put it in a different circuit, and that circuit may cause some bias with VDS equals to 5 and VGS is 2 volts. Then I know that the current that will pass through the transistor is going to be 600 microamps. So this is the situation. Okay, now I go back here. Now I can also do simulation with two things. For example, here I am sweeping gate source voltage. Sweeping tu maksudnya from 0 to 0.001, 0.002, 0.003, and that will form the X voltage up to 2 volts, which is the N value which I have defined here. But I can also do a step. Okay, let's have a look at okay, now this one has a step. So if I do my edit simulation command here, I have a first source that I sweep, which is VGS DC, and I have a second source which is VSB. So what I'm going to do here is that I am sweeping VGS from 0 to 2 volts in small values. Let's have a look what the increment is for first source. No, I have not mentioned, so it will take the smallest increment. But then for the second step, once it has gone through from 0 to 2 VGS, it will go on to the next value of VSB. So the first value of VSB is 0 volts. So it will go from 0 VGS to 2 volts VGS. Dah habis tu, it will go on to the next VSB. So VSB di sini, okay, we say it will go on increment. So it will go on to the next VSB, which is 1 volt. Then it goes from 0 to 2. So let's see how it goes until it goes up to 5 volts. Okay, so I will now add ID M1. Nampak tak? It starts with from 0 to 2. I might as well put the legend here. I can view the legend here. I can select the steps, or I can also have all the steps and I can have the legend here. Okay, so the black one is the black plot is VSB equals to 0. But if VSB is equals to 1, the blue plot, okay, it shows that the plot ID versus VGS has shifted. It means that the threshold voltage has changed. From 0.8, for example, maybe it has changed to 1 volt. So with VSB, we see this effect of the threshold voltage shifting. Okay, so what I'm showing to you here are two things. One is how to play around with LT Spice, because we can play with sweep and step. Okay, that's one thing. Here we sweep VGS, we step VSB. And the second thing that I'm trying to show here is that when you connect your NMOS to different parts of the circuit, where sometimes the source may not be connected to ground, but the bulk is always connected to ground. So there's going to be a difference of VSB. There's going to be a difference between source and bulk. You will expect that there will be a shift of threshold voltage. So if you look at the model, if I look back here, if you look at the model here, it says VTO. VTO. This is threshold voltage when VSB is 0 volts. It means that this is the threshold voltage when there is no difference between the source and the bulk. But when there is difference between the source and the bulk, then the behavior is going to be slightly different. Then in this case, you will look at a different value to see how it's going to function. You won't see how exactly it affects by the value, because you're not going to do the calculation. The simulator will do the calculation, but you might have something that is affected by this value here, gamma. Okay, and this gamma here, for example, 0.5 will do your calculation for you and will give the behavior in the simulator that looks like this. Okay, this is sweeping from stepping from 0 to 1 to 2 to 3 to 4 to 5, okay, for VSB. And for each of the step of VSB, VSG is swept. So there's sweep and then there's step. I'm back to the slides. Just now we did the connection to get the transfer characteristics. Transfer characteristics pun salah kan? Sekejap we have our characteristics. Okay. Now, what if you look at the name of the plot, it's transfer characteristics. It means that what you're doing here is not designing an actual circuit. You're doing a characterization. You want to see what the characteristics of the NMOS and PMOS is. Okay, so this is transfer characteristics. When you put in a signal, input signal, what do you get from the output? Okay, and what do you get? You get to see that if your input signal is less than threshold voltage, there is no current here. And if you apply VGS greater than the threshold voltage, then there will be current. So just now we saw NMOS. We'll have a look at PMOS. Very quickly, I have here, this is still NMOS. Let's have a look at PMOS. Okay, so this is PMOS. Now when I have PMOS, when I add PMOS, I need to rotate it. You can use Control R and Control E to rotate the PMOS. So that source is at the top, drain is at the bottom. And then you have here, I have connected VSG and VBS for the body effect. I have defined, when I did the simulation command, I have defined that I want to do VSG going from 0 to 5. So when it is 0, when VSG is 0, it means that the input to the gate here is going to be 5. Okay? So if VSG is 0, because it's VSG is VS minus VG. So when it is 0, it means that the input is 5 volts. So 5 minus 5 is 0. And then when VSG is 5, it means the input is, the actual input, the VG, is going to be 0, because 5 minus 0 is 5. Okay, so I can plot this, and when I plot for my PMOS, I'm going to plot, if it's just easier for me to show you, right? If I add traces, if I put in drain current, because of the notation of yang kita terbalik tadi kan, okay, because of the notation of the drain, it will give me ID versus VSG yang terbalik. Okay, because it's actually giving me this current and it's giving me the current that is going in. Okay, because the definition of drain is the current that goes in, and if it's the current that goes in, it is actually current yang naik sini. Okay, so I need to not, okay, I can use the scissors to erase this. I need to add not ID, but if it's a PMOS, I want to add IS. Okay, there you go, IS. Okay, and IS, it turns on, let's have a look at our PMOS. If it's a PMOS, the threshold voltage is about 0.9. Okay. Okay, because this Y here is slightly shorter, so kita nampak macam baru kita nampak lah dia tak berapa naik, dia dah mula naik dah. Okay, this area is called the subthreshold current. We have the same thing with NMOS. Okay, but for PMOS here, it's the same thing. We can plot this. I just want to show you that you can plot this with PMOS as well. Okay, now I want to go back to this slide. Okay, so this slide is settled. I showed here the graph here. This yellow one is when you're just plotting VSB equals to 0, but if you step the VSB, you get these pink values for NMOS. I'm not doing it for PMOS because it's a bit more complicated. Okay, because we just want to see how to use it in UiTM. Now the same thing with transistor characterization, we can also have output characteristics, which is ID versus VDS. Okay, this plot, if you remember, if you've done the lab, you can get this family of curves as well. Okay, so here at the top part here, I have configuration where I connect the transistor, the NMOS transistor. In this case, the bulk is going to the ground. Okay, here I tak letak VSB dah, I just directly connect it, okay, because I don't want to sweep VSB anymore. Okay, and here, if I look at this plot here, if I know that I want to plot output characteristics, I have to look at the curve, the plot, and look at the x-axis and the y-axis. The x-axis is VDS. Okay, transfer characteristics tadi, the x-axis is VGS. Now the x-axis is VDS. Okay, which means I'm going to sweep VDS, not VGS. I'm going to sweep VDS from 0 to 5 volts. And then I'm going to step. Okay, I'm going to step it at VGS from 0 to 5 volts. So 0, kita tahulah VGS goes to 0, it's not going to be greater than threshold voltage, right? But at 1 volt, dia dah mula ada. So I can step this to see how it's going to step. Now this plot that I show here is not the results for this simulation, but I'm just putting it here together so that you see what it's going to look like. Now, if I sweep this, if I sweep the simulation, UiTM for PMOS, okay, it's the same thing, but I have source at the top, so I'm going to do .dc for VSD sweep, and the step will be VSG. Now, when I plot, if I, again, like I mentioned just now, if I do not state IS, but I state ID, dia akan terbalik macam ni. Okay, now let's have a look. This is, let's have a look. This is, okay, here you go. This is an NMOS. Okay, so I'm going to, let's have a look at this edit simulation command. What I'm doing is that I have a first source. I'm going to sweep VDS from 0 to 5 volts. Sweep 0, 0.1, 0.2, 0.3, 0.4 sampai 5 volts. And then when I'm done, I'm going to take the next step. So the first step will be VGS equals to 0 volts. The next step, once I finish from 0 to 5 for VDS, my next step will be the second source, the increment by 1 volt. So next one, VGS is 1 volt, and I sweep 0 to 5. Next step, I go to VGS, I go to 2 volts, and I sweep from 0 to 5 again. It's a small step, 0, 0.1, 0.2, 0.3. Sampailah I step until 5 volts, then I still do 0, 0.1, 0.2, 0.2, sampai habis VDS tu, then I get all my plots. Okay, so now let's run this. I'm going to add traces, and this is going to be ID of M1. So the one below, tak nampak warna hitam tu. kat bawah sekali ada warna hitam, kita tak nampak. Yang hitam tu is when VGS is 0 volts. The blue one is when VGS is 1 volt. The red one is when VGS is 2 volts. Green is when VGS is 3. Pink is when VGS is 4 volts. And the grey plot is when VGS equals to 5 volts. So this step kan. But for each of the step, it will split it to give you the x-axis from 0 to 5 volts. And it will measure the current. So what do you get from here? What you get from here is that you know, for example, I want to operate this transistor in saturation. For example, where VDS is 2.5 volts. Yeah. Katakanlah VDS is 2.5 volts. And I want to bias VGS to be equals to 3 volts. I know that if I have that transistor put into that circuit, complicated circuit with that kind of biasing, the current that I will have through the transistor is going to be about 1.3 milliamp, for example. Okay, itu tujuannya characteristics. Kita nak plot dia supaya kita faham behavior dia. Once you get the behavior, then you can determine how the transistor will behave when you take it and put it into a different circuit. Okay, so going back to the slides. Now, next question is, so what happens if it is a different technology? How does the 1 micron technology differ from the 50 nanometer? There will be, if you take the transistor and put it in a circuit, you will see a lot of difference. But let's just have a look at the most basic transistor characteristics. Okay, so here I am showing you the model for the 50 nanometer BSIM4. It's, the font is very small, you don't need to see what it is. Okay, but just sufficient for you to see that when it's smaller, it has to be described with more complicated and engaged equations, and therefore you have going to have a lot of parameters. Okay, so this is the 50 nanometer, which is described not using the level 3 model but with the BSIM4 model, which is a level, I can't remember, level 54, something like that. Okay, so I'm going to do the same thing. I can do the same thing, ID, VGS, transfer characteristics, ID, VDS, output characteristics. Okay, I can have the same value of W over L effectively becoming 10 over 1. But in this case, my transistors here are not 10 micron to 1 micron, but 500 nanometer to 50 nanometer. So let's have a look here. 500 to 50 nano, so it's still 10 to 1, right? 10 over 1. And the name of the transistor here is N_50N. Now we'll have a look at the simulations a little bit in a little while. But if you see here, the current values here are going to be slightly different. Okay, I sweep here not from 0 to 5, but in this case I'm going to sweep from 0 to 1 VDS, because when the transistor becomes smaller, VDD supply can also become smaller. So I don't have to sweep from 0 to 5, and the transistor will only perhaps need a VDD of 1 volt. So I'm going to sweep from 0 to 1. Okay, so let's have a look how this is different. I'll have to, hang on. Let's compare this with this one here. Okay, so now I have here, I'm showing you here the same circuit as the one here. Okay, the one previously, the previous simulation that we did, the name of the transistor is N_1U. So when we look at the name, when we look at the model, it knows that it has to find the name N_1U, which is the 1 micron meter technology. But for the 50 nanometer technology, I've already told the simulator that the name of this transistor is N_50N. So it's not going to take N_1U because that's not the name. It's going to find N_50N, which is too small here for you to see, but later you can see. This transistor will use the 50 nanometer model. Okay, now the size here is going to be 500 nanometer over 50 nanometer, which is still 10 over 1. Okay, and I'm still going to sweep VDS, because this is output characteristics. I'm going to sweep VDS at a step of VGS. But here I'm not going to step from 0 to 5. I'm just going to step from 0 to 1, because this is a smaller transistor, much smaller transistor, smaller technology, and therefore the power supply will also be much smaller. Okay, so let's do a run here. Add trace, we're going to add ID, because M1. So you can see this from 0 to 1, which is the range of the power supply, the current goes from 0 to about 300 microamps. So if I say, let's say my VDS is 0.4, VGS is 1, the current that we expect is about 240 microamps. Okay, with my 50 nanometer transistor. But if I were to use the 1 micron transistor with a VDS of 0.4, at 0.4 VDS, the transistor will be in the triode region. Tapi tadi 0.4, 50 nanometer, dia dah saturation region. Here it is still in the triode region. If VGS is 1 volt, yang mana entah 1 volt, so I cannot remember, so I'm going to use the legend. VGS 1 volt is this blue value. Okay, so it's still going to be in a region here. Okay, and the value will not be the same. I don't know what the value here is. Hang on, but you get my message. The behavior will be different. Okay, I'm going to go back to here. Now you can explore other things. Like for example, what happens if it is a different W of the same technology? Not in a different W over L. No, not a different technology. Okay, let's say you want to still look at, you still want to use N_1U, which means that you want to still see the 1 micron technology. Okay, but in this case, you want to see what the effect of W is. I can change W tadi, W kita letak 10 micron kan. Let's say I want to do 20 micron. Or I can play around with LT Spice. Okay, this I did not know that there was a syntax. But usually all the simulator, all these tools, there will be some tricks, or there will be some steps. There will be some instructions on what to do if you want to investigate, you want to do some research. Okay, so in this case, LT Spice, I saw in the internet, it says that if you want to step the parameter, I can define the whatever parameter I want in curly brackets, and then place it, and then do another step parameter. So for example, I have here, okay, L is 1 micron, W yang tadi 10 micron tu, now I've put W in curly brackets. Yeah, I'm going to sweep VGS from 0 to 2 volts, but with this curly bracket, I'm going to tell simulator, the simulator knows. Now take this curly bracket, do a step parameter from W, start at 10 micron, finish at 100 micron with an increment of 20 micron. So what I have here, okay, I will have the black plot. Okay, here W is 10, but as I add 20 micron to the blue plot, 40 micron to the red one, green one is 10 plus 20, 30, and then 15, and 70 micron, and then 90 micron, and I finish at W equals 100 micron. Okay, now I can see that if I change the W, I can see that the larger W increases the on current. Okay, so these are things that you have to be comfortable. To know observe this yourself, how W over L changes, how the technology changes. So you can explore LT Spice on your own. Mentor Graphics, sorry, this is Siemens EDA, right? But you know what I mean. Siemens EDA has a fixed model, so you can explore W and L effects in S-Edit as well. Okay, have fun. I'll see you on Tuesday, inshallah, 9 o'clock. Assalamualaikum.